welcome you,
Thank you,
ma'am.
sir.
And she will deliver the 2 sessions. One is on transportation problem, and second is on traveling salesman problem. So please, ma'am, you can.
Very good morning to everybody.
Good morning, madam.
Good morning, Ji. Before I start I have to deliver talk on transportation problems and transportation. Is it okay? I think I'm audible.
Yes.
Transportation problems and traveling salesman problem. So before I start, let us look at what is operational research. So because that is a wide topic under which all these things lie. So operational research is a systematic and scientific study of operations of a system. Basically, it deals with analytic methods for problem solving and decision making, which is useful in management of organizations. So whatever managerial problems are there or decision making, wherever decision making is involved, so that is all taken care of by.
Support them.
Okay, fine. So all such kind of things are taken care of in this field. Basically, the main problem is broken into base components, and these base components are then modeled, and then procedure, that is problem solving, is done. So what are the applications of this? Let us see. So applications of OR. This has applications in almost all the areas. यहाँ सारे लिखे नहीं हैं, many more as it is written. Name any field where it doesn't get utilized. So let it be finance, let it be marketing, let it be industry, let it be medicine, let it be pattern classification, let it be transportation, networking, everywhere. War, actually the origin of this field is from World War II. So this name also originated, operations, that was actually related to military operations. So from there the name came as operations research, right? So it has applications in wild fields. Then there are two, as I mentioned, there are 2 stages. One is you model a problem. So main thing is how we are modeling a problem, or different, how the main problem is broken into base components, and then they are modeled. And then looking at the format of the problem, then we decide how to solve it. What is the solution strategy of the problems, right? So depending upon whether the mathematical expressions in the problem are linear or non-linear, the problem will be called as a linear or a non-linear programming problem. I won't go much into detail of non-linear because transportation problem is in the category of linear programming problems. So let us take this example in particular. I won't say initially whether it is a linear programming or a non-linear programming. So let us look at this. A manager of oil refinery must decide on the optimum mix of 2 blending processes, of which the input and output production runs are as follows. So process 1, it uses input as crude oil A, crude oil B, and it gives gasoline X and Y, and these are the units mentioned for process 1 and the units mentioned for process 2. Then the maximum availability of crude A and B are given. Minimum units which should be produced of gasoline X and Y are also mentioned. Then the profit per production run of processes 1 and 2 is 4 and 5. Now these days rupee 4 and rupee 5 is actually, it should be modified to something, rupees की जगह कोई और currency आप assume कर सकते हैं. So then the problem is here, how to get the optimal mix of both the, how to get the optimal blending of both the processes to meet these outputs by using these inputs so as the profit is maximized. So here this problem is that the decision making, basically it is the number of production runs, how many production runs of process 1 and how many production runs of process 2 should be there, so that when you blend to get these outputs, then the profit is maximum. So how do we formulate this? Let us see. First of all, is it a linear program or a non-linear program? Let us see that also. what we have. Let's write x1 as number of production runs of process 1, x2 be number of production runs of process 2. Can we formulate the problem now? If 4 and 5 are the profit per unit per production run of process 1 and 2, then what should be the profit function which we want to maximize? So yeah, we want to maximize 4x1 plus 5x2 subject to the condition that when you are mixing the two, so it means that 4x1 plus 5x2. Now this maximum amount available for crude A is 250. Then for crude B, sorry, this is, I have written 4, this is 6 for crude A. Then 4x1 plus 6x2, this should be at the most 150. And the gasoline ke liye minimum amount which should be produced, 5x2, this should be at least 150, and 9x1 plus 5x2 should be at least 130, x1 and x2 should be 130. So this is a problem which we have modeled using this, and so this is a good example of industry, right? Mixing of gasolines. So this is what I wanted to model. Then let us see further. Okay, so I'll come back to this slide later on. Let us look at the format. So basically this is a linear program, as we all know why this is a linear program, because the function which is being maximized, that is linear in the decision variables x1, x2. The constraints are linear inequalities in decision variables x1 and x2, and decision variables are non-negative, right? So here, although here the problem mentioned the general form of linear programming problem with n variables and m constraints. Each of these, how many constraints are there? There are 4 constraints here. x1, x2 non-negativity is not a constraint. That is a non-negativity restriction. Constraints are 4 and variables are 2, right? So in general, if there are n decision variables and there are m constraints, then the form of linear programming problem is this. Now you can say that y equation, here we have inequalities. In this case, one thing I want to express, say if I take any one of them, in general my linear programming is maximize or minimize. You will have C1 x1 plus Cn xn subject to A11 x1 plus A1n xn B1. It could be any of them. Similarly, it could be less than equal to, I mean this notation is that it could be equation or inequality as you have seen in this example. But then why are we taking the format to be as equations? Because this will come later on while we are discussing only in the form of equations, but definitely this can be made equivalent to that form. Why it can be done? Say in this case, if I take this example, then suppose I'm just taking one constraint, similar treatment can be given to others. You can write x3 as 250 minus 6x1 minus 5x2. This non-negative is the same thing as writing this constraint. So this equivalently, I can write this as 6x1 plus 5x2 plus x3 is 250, where x1, x2, x3 is non-negative. So we are introducing something which was short of, is called slack. So you are introducing slack variables for constraints which are less than equal to type. Similarly, the constraints you had greater than or equal to, you are going to subtract something surplus. So those are called surplus variables. And therefore the whole system of inequalities, if there, can be converted to system of equations. So without loss of generality, you can assume your linear program to be in this form. Because if there are inequalities, you can convert them to equations by introducing non-negative slack or surplus variables as per whether the constraint is less than equal to or greater than or equal to types. This is okay. This is what we generally do with the problem, given the problem. Now, so we assume this to be the main model because every problem can be reduced to this problem. Okay, then since the topic under discussion is an LPP, so we must know basic properties because those properties will be used in solving the transportation problem also. So for the properties we need some concepts. So let us come back to the previous slide. This convex set. What is a convex set? We need all these terms. You all are familiar with the convex set? No? Okay. Convex set is a set. Since we are working, अब देखिए ये जो problem बनाई थी हमने अभी, how many variables it has? 2 variables, right? If you convert it into equations, how many variables you are getting? 4 more variables, 2 slack and 2 surplus. So we have 6 variables. So when we are solving a problem in 6 variables, it means the set of feasible solutions here is basically, of course, I must define what do we mean by set of feasible solutions. For this problem, what do we mean by set of feasible solutions? Solutions are those x which are satisfying Ax equal to b. So since there are n variables, x is in Rn. If this x is satisfying this condition also, x is non-negative. Non-negativity is also satisfied, then it is a feasible solution. So every solution may not be feasible, but every feasible solution will definitely be a solution, right? And then out of all, that solution which is giving the maximum value of objective function is optimal feasible solution, and I have that in the next slide. But I need this discussion because the set of feasible solutions here, agar aap plot kare, it's going to come out like this. Graphically, when you solve a 2 variable problem and you plot those inequalities, you get a region of this kind, right? So this is the set of feasible solutions, right? And this has infinitely many points in it. So how do we check which point is? It means set of feasible solutions. देखिए feasible means 2 variables में first quadrant में lie करेगा region and points lying inside the. This is denoting one constraint. These inequalities are giving you, intersection is giving you this region. This is the feasible region of the problem. So there are infinitely many feasible solutions. Problem is how to find the best out of them. Best may be unique, best may be, again, infinitely many. You agree that best could be infinitely many? Suppose you have best here and best here, then this whole edge is best, because this is the line segment joining these 2 points. So basically, we are going to exploit a property here for solving an LPP, that solving on this, searching for optimal solution here, means we have to move only on corner points. But corner points किसके exist करते हैं? हर set के corner points नहीं होते हैं. If you have a curve like this, it doesn't have a corner point. So these points are in context to convex set. This region is a convex set. First of all, this is first property, that set is a convex set. What do you mean by convex set? I don't want to spend much time with this because transportation में काफी time लगेगा. But before that, I have to tell. Convex set is a set. Do you want me to write the definition or just explain? Convex set, you pick up any 2 points, a set S in Rn. मैं Rn की बात इसलिए करी क्योंकि in general हम assume करें कि हमारे पास n variables है. If you have a 2 variable problem, then this set of points, these are all ordered pairs, these are in R2. If you have n variable problem, then set of feasible solutions is going to be, in general, you talk of any set, it's going to be subset of Rn, right? So let S be any subset of Rn. If it is an empty set, then by default, we assume it to be convex. If it is non-empty and it is a singleton set, again, since it has only 1 point, we take it to be convex. If it has more than 1 point, it means it has at least 2 distinct points, x and y. we say S is convex if lambda x plus 1 minus lambda y belongs to S for every lambda 0, 1. What does this denote? This is nothing but the line segment joining x and y. For lambda equal to 0, you are at point y. For lambda equal to 1, you are at point x. And for every value between 0 and 1, you are in between the 2 points. So set is said to be convex if you pick up any two different points, any pair of two different points in S, then the line segment joining those 2 points must again lie in S. So say this is a convex set. इसके अंदर कोई भी 2 points ले लो. Circle in particular in 2 dimensions, a point itself in 1 dimension, okay. Then an interval on the real line. These are all convex sets. Well, any polyhedron is a convex set. Then we think of a set which is not convex. Parabola is convex. By parabola I mean closure and closure of the parabola, or even in this simply the interior. But is the boundary convex? If I have a parabola, या ऐसा ले लो, कैसा भी ले लो parabola, क्या इसकी boundary convex है? Means you pick up, you can always find, in fact you pick up any pair. Non-convex show करना, you just have to show the existence of one such pair for which. But here you pick up any pair, you see that the line segment joining them doesn't lie on the top. So this is not a convex set. Then a circle, interior or closure of a circle is, but boundary of a circle, only circumference, not convex. And you can, if you take an annulus, that is 2 concentric circles, the region between 2 concentric circles with different radii, then you see this region is not convex because you take any point here, you take a point here, line segment joining them does not lie inside. So you have infinitely many examples of both kinds, convex as well as non-convex. I won't go much into detail. But you can say any solid having hole in it will definitely not be convex, right? So first observation, these are the results. I'm not going to prove them, but some concepts I'll discuss with you, and main results I'll discuss. I won't go into the proof making. That the convex set we already know. Then what is convex combination? If I talk of 2 points x1 and x2, then lambda x1 plus 1 minus lambda x2 for every lambda in 0, 1. Or this is the convex combination of x1 and x2. That's the line segment joining between them. This I can also write as alpha 1 x1 plus alpha 2 x2, where alpha 2 is 1 minus alpha 1, alpha 1, alpha 2 non-negative. Same thing I can write. If I want to generalize it, suppose I want to talk of such a combination of finite number of points more than 2, say k points, then what will be convex combination of k points? That will be sigma lambda I xi, I1 to k, where sigma lambda I is 1, I1 to k, and each lambda I is non-negative. Same thing as this. So this is a convex combination, right? So then I come to hyperplanes, because all these things are needed here. What is a hyperplane? Hyperplane is set in Rn such that z equal to cx. C le lijiye, A le lijiye. You can, where C is a vector in Rn which is given to you, and z is a scalar again given to you. It means if I talk of line 2x1 plus x2 equal to 1, collection of all those points x1, x2 which satisfy this equation, what is that? That's a line. So in R2, line hyperplane is a line. In R3, it is a plane. In Rn, it is a hyperplane. So this is the definition of a hyperplane. So when we talk of, this, then there's a property that intersection of finite number of convex sets is convex. Intersection of finite number of closed convex sets is convex. As from the definition, this we can prove it's a convex set. Each hyperplane is a convex set, and each hyperplane is a closed set. So since they are closed and convex sets, so this is a closed convex set. can be proved by definition. Then intersection of finite number of hyperplanes will again be a closed convex set. So when I go back to the formulation of LTP, maximize or minimize Cx subject to Ax equal to B, X non-negative. What are these? X which satisfies all of them simultaneously. This is, of course, this is a closed half space. ये भी मैं आपको बता दूंगी. These are all hyperplanes. Each equation, X satisfying each constraint means what? It means intersection of M hyperplanes. When I go back to this one, see here, these M constraints are what? Each one of them is a hyperplane according to our definition. And we want X satisfying each one of them. It means set of solutions is what? It is the intersection of finite number of hyperplanes. And we've just seen that these hyperplanes are closed convex sets, and by property intersection of them is again a convex set, which is going to be closed. Therefore, this set of solutions is a closed convex set. And this is in positive quadrant. In our case, in case of two variables, it is the first quadrant. So basically, X non-negative जब आप लगा देते हैं साथ में, so this becomes a closed convex set in first quadrant in case of two variables, right? And same way in the positive quadrant in case of more variables. So this is what we have. Otherwise, also you can analyze further. These are nothing but closed half spaces. मैं इस detail में जा रहा. X non-negative. Actually, this is of the type. If you have Rn, this can be written as S1 union S2 union S3, where S1 is X such that Z is Cx, S2 is X such that Z is greater than Cx. ये तो clear है ना? Logic. Pick up any X in Rn, either it will satisfy this, or it will satisfy this, or it will satisfy this. Whole of Rn can be written as a this is mutually exclusive and exhaustive union of Rn. So this is hyperplane. These are called open half spaces because these are open sets and these are half spaces. In R2, what is this? If R2, this is the line Z equal to Cx, hyperplane is a line in R2, then Z greater than Cx is this part. मतलब कोई एक greater है, कोई एक less है. तो पूरा R2 जो है, that is divided into one open half space, another open half space, and the line. In Rn, the same thing. So these are called open half spaces. Again, if we put these things, then S1 is nothing but intersection of S2 and S3. Or in other words, you can say that if you include the line also, then this becomes a closed set, closed half space. This is again a closed half space, and this line is the intersection of the two closed half spaces. It can be again proved that these closed half spaces are also convex sets. So here, if you look at that problem, then Ax equal to B is already intersection of finite number of hyperplanes. Then X non-negative, this is intersection of closed half spaces. Now, these are again closed convex sets. When you look at the whole set of feasible solutions, what is that? That is intersection of finite number of closed half spaces and hyperplanes. And all this intersection is again a closed convex set. So the first thing we have is that this set of feasible solutions of LTP is a closed convex set, right? And it is bounded below by 0. So once we have a convex set, we talk of extreme points. And by the way, what are polyhedron? We say, आपने ये word बहुत सुना होगा कि polyhedron होता है. LTP का जो feasible set है, that is a poly. What do we mean by polyhedron? Any figure like this, having finite number of edges? What is the basic definition of polyhedron? Polyhedron is intersection of finite number of closed half spaces. So we have closed half spaces. Closed half spaces में hyperplane भी आ गए. So whether you have this kind of thing or you have this kind of thing. In either case, set of feasible solutions of an LPP is the intersection of finite number of closed half spaces. Therefore, it is a polyhedron. And if a polyhedron is bounded, अब ये bounded है, therefore it is a polytope. There is a difference between polytope and polyhedron. Bounded polyhedron is called polytope. If I talk of this is also a region, feasible region, but this is unbounded, and this is the intersection of two closed half spaces. But here this region is not bounded. So this is a polyhedron, but not polytope. So in general, the set of feasible solutions of LPP is a closed convex set, bounded below by 0. It's a polyhedron. It may be a polytope. It may not be a polytope. So this is why we need these terms. And above all, graphically आप लोगों ने करे problems simplex method से. Simplex method से नहीं, I mean graphically you have done. तो उसमें optimal solution हमेशा पहली चीज तो boundary पे आता है, दूसरा किसी ना किसी corner पे आता है अगर exist कर रहा है. So for this set now we need to define what we mean, because in transportation problem we'll be moving from one corner point to another corner point. So what do you mean by corner point? How do you define a corner point? Corner point पहले तो in context to a convex set. If the set is not convex, we can't talk of a corner point. So what is an extreme point? These are called extreme points. What is an extreme point of a convex set? How can we define it? नहीं, आप R2 में तो कह देंगे corner है, Rn में you can't see it graphically. So what does corner have? Corner has no meaning in Rn. So but what is the typical property which is being exploited by a corner point? It means that if a point of a convex set is a corner point, first observation it is going to be a boundary point. Interior में नहीं हो सकता. क्यों नहीं हो सकता? Because it cannot be written as, it cannot lie on the line, strictly on a line segment joining any other 2 points of the set. Can you make it lie on the line segment joining any other 2 points of the set? Suppose I take this point and this point. All the points lying on this, none of them is a corner point. ये corner point की एक बहुत strong condition है. This is the only thing which distinguishes it from the other points. It cannot be made to lie strictly on the line segment joining any other 2 points of the set. See, this point is not a corner point because it lies on the line segment joining these 2 points. This is not a corner point, but this is a corner point and you can't make it lie on the convex combination of strict convex. Strict का मतलब हो जाता है when lambda is, you are excluding the 2 points. That point itself can be one of them. मतलब आप इस point को किसी भी 2 corner points की strict के बीच में नहीं लगा सकते हैं. उनमें से कोई एक हो सकता है वो, but बीच में नहीं हो सकता है. So extreme point. So if x star is an extreme point, is an extreme point of S if there does not exist any pair of distinct points. Of S such that x star can be written as lambda x1 plus 1 minus lambda x2 for some lambda in open interval 0, 1. This is the mathematical way of saying that a point is an extreme point. You are not able to find any other pair of 2 different points of the set such that this point can be made to lie strictly on the line segment joining those 2 points. So all such points are corner points. And so what are the properties now? Main property of LPP, that is, if the problem is feasible, if the set is non-empty, then definitely it has at least one corner point. And optimal solution never occurs in the interior. It occurs on the boundary first of all. And on the boundary, even if it occurs on boundary, suppose this whole edge is optimal, but at least one of the corner points will be optimal feasible solution. So that is the property which helps us in exploiting this. So main properties. First observation, OFS, optimal feasible solution, is at least one extreme point of this. And as we can see graphically, extreme points are finite in number. So problem becomes very simple. You don't have to travel on these edges. You don't have to hunt the interior. Just look at the corner points and see where the best value you are getting. You stop there and you declare that point to be optimal point. But the graphically seems to be very good. But when it comes to the actual problem formulation of M cross N system, because set of feasible solutions is in terms of M cross N system of equations now, then how do you see an extreme point over there? तो ठीक है कि आप extreme points देख लेंगे जिसपे best value उस पे चल जाएंगे. So then we get the concept of basic feasible solution. Actually, in order to start the algorithm, I have to discuss all this. Basic feasible solution. Basic, when you have this expression, हम एक चीज ले लेते हैं, maximize या minimize. Suppose because minimum of f is nothing but minus maximum of minus of f. So you can convert a minimization to maximization and so on. So if you have this thing subject to ax equal to bx non-negative, right? Then we'll define, we already have the concept of feasible solution. It means I have the whole set here. This is my x equal to bx non-negative. I want to talk of these points here, which are extreme points. They correspond to basic feasible solution, as the term comes from there. Basic feasible solution of the system. So BFS of this system, that is basic feasible solution, identifies a corner point of the region which you, because not always possible to plot the region in case of big problems. So BFS, then how do we define a BFS for a system? See, one thing is, this is main result of the LPP. Second result says there is one-to-one correspondence between BFS and extreme points. And third observation is extreme points are finite. वो यहाँ से दिख रहे हैं R2 में, Rn में कैसे justify करोगे आप, right? What we'll do is, we are assuming this is R, but we ought to know what is a BFS. Given a system, how do we find a BFS? How do we define a BFS? Then knowing that there is one-to-one correspondence, if we can justify that number of BFS is finite, we'll immediately tell you that the number of extreme points is finite. So moving from one BFS to the other BFS here means you are moving from one extreme point to the next extreme point. So you're just hunting the extreme points. So how do we define a BFS? If you have the system Ax equal to B, M cross N, you can assume M to N, and suppose rank is M. I'm taking a simple case. Rank कम हो तो उस केस में भी आप define कर सकते हैं. If rank is less, then some constraints will get redundant. So you are left with the reduced system. So if it has full rank, you agree with that? Suppose here it has A has M rows and N columns. N is less than equal to N, so rank A can be at the most 10. If rank A is K less than M, then we know that M minus K constraints become redundant. So you can solve the reduced system K cross N. And again, in that case, it comes to the same form as you have this, where M cross N system, M less than equal to N. So you have rank equal to M. So if this is the case, it means that there exists an M cross M non-singular submatrix of A. If rank of A is N, you can partition A as, now I have the system Ax equal to B, this I can write as Bn, xb, xn equal to B. I am separating the columns corresponding to B. N minus M columns जो बाकी बचे जो इन पे linearly dependent होंगे, these I am writing as the collection capital N. X variable के जो variables इनके साथ connected है उनको मैं xb कह रही हूँ, जो इनके साथ connected है उनको मैं xn कह रही हूँ. So when I solve this, it becomes bxb plus nxn equal to B. Now I give different values to xn, I get different. What is b xb from here? That is b minus nxn B inverse. Is it okay? I can define XB. XB vector में कितने components हैं? M. These M variables I can define in terms of these N minus M variables. You give different values to this, accordingly you get a unique value to XB. These are dependent, these are independent. So then you take these variables equal to 0. Then the solution to the reduced system is called a basic solution. If you give Xn, vector Xn has how many variables? N minus M variables. I am setting them all equal to 0. Then this system becomes Bxb equal to B. ये वाला system reduce हो जाएगा. Set Xn equal to 0. Implies this. Then the solution to this system is this. तो Ax equal to B का जो solution हो गया वो क्या हो गया? That is going to be Xb, which is B inverse B, and Xn is a 0 vector. Then such a solution is called a basic solution. And if all these components are non-negative, then this becomes a basic feasible solution. So, and how many such can be there for a system, M cross N system? Got the concept of basic feasible solution? Means आपको system दिया हुआ है Ax equal to B, आपके पास rank AM है, select a capital B which is non-singular of order M, and accordingly you solve the system Bxb equal to B. Then we know B is invertible, so this has a unique solution. So basically these variables are the basic variables and such a solution is a basic solution. Now these may take negative values, these may take positive values, these may take some of them may take 0 values also. When all are non-negative, then this solution becomes a basic feasible solution of the system. Now the question is, we assume that this is a standard result, that there is one-to-one correspondence between the extreme points of the region and basic feasible solutions of the system. So moving on, corner points, the same thing as moving from one BFS to next. This is what simplex method does. It takes us from one extreme point to other by moving from one BFS to the other. But how many BFS will be there? Maximum कितने होंगे? You have this M cross N system. बता सकते हैं? Corresponding to कोई भी BFS जो है, that is actually characterized by this matrix. आपने ये matrix select करी, vector B is already given to you in the system X equal to B. You have for a different choice of capital B, you will have a different XB. It means in how many ways you can select M non-singular submatrices out of, M cross M non-singular submatrices out of a matrix which is M cross N. या तो ये possibility क्या हो सकती है? It means there are M columns out of N columns. पहली चीज तो वो जरूरी नहीं कि you pick up any collection of M columns out of N will be linearly independent. But what is the maximum I'm saying? ये जो basic solution है, this is going to be a subset of in how many ways you can select M columns out of N columns. Because this has M columns and A has N columns. So B may be A1, A2, AM. B may be any set of M columns out of these N columns, which is non-singular. Maximum कितने हो सकते हैं? Maximum इससे कम ही होंगे क्योंकि जरूरी नहीं कि सारे इस तरह के सेट जो है वो linearly independent है. But ये upper bound है ना? So at the most, the number of basic feasible solutions can be NCM. So this is finite. So for any system M cross N, maximum number of basic feasible solutions can be NCM in number. Therefore, there will be finite number of extreme points in the set of feasible solutions, right? And therefore, optimal solutions, if exists, that will be attainable by simplex method. So then we come to, once we have these things in our mind, we come to transportation problem. Transportation problem is basically, again, it is a linear programming problem. I'll go to the slide of transportation problem now. Transportation deals with the, as the name suggests, main thing. This is the transportation problem. So you have M sources and N destinations, and transportation of some homogeneous quantities being done from these sources to these destinations. One thing is clear that the quantity is the same. ऐसा नहीं कि एक ट्रक जो है ऑयल लेके जा रहा है, दूसरा ट्रक जो है वो एग्स के क्रेट लेके जा रहा है, नहीं. अगर सारे ट्रक एग्स लेके जा रहे हैं तो सारे ट्रक एग ही लेके जा रहे हैं. Quantities are the same. Let me tell you one thing more here. When the quantities also differ, then this again is a transportation problem. I'll come to that later, but first let us see the basic structure. That is also a very interesting part. So here you could take these sources to be, you could take them to warehouses. Then you could take destinations to be retail shops, markets, material being transported, right? And AI is the amount of that product available at ith source, BJ is the requirement of the product at the jet destination. So this is the data which is given to you. Then transportation problem is of two types: cost minimization and time minimization. So first I'll discuss the format of cost minimization with you. Once we do cost minimization, let me complete the discussion on time minimization also. This is the format I'll explain what do you mean by time minimization. And the time minimization problem can be solved using, you can convert time minimization to cost minimization. And for that, these are the ready references. थोड़ा सा आपको बता भी दूंगी कि time minimization. But then, what do we mean by time minimization? What do we mean by cost minimization here? So let us come to the basic. I mean, time minimization is just a variant of cost minimization. So once you understand how to be solved cost minimization, you can go on to solving time minimization. So here Cij is the cost of transportation of 1 unit of that quantity from ith source to jth destination. And here actually this problem which I have mentioned here is a balanced problem, because the constraints, these are sigma xij equal to ai's. These are source constraints. These are destination constraints. Because this says that from each source I, the amount which is xij is what? Xij is an element which is being transported from ith source to jth destination. So these the constraint says that whatever is being supplied from the ith source, whatever being is transported from ith source, that should coincide with the amount which is available at that source. And the second part says that whatever is the amount which is being received by the jet destination should exactly coincide with the requirement, right? So this is a very simple, you can say this is the simplest form of a transportation problem, and our aim is to minimize the total cost of transportation, right? So here this cost doesn't always mean cost. I mean money, it could be time, it could be distance. So you have, this is a symbolic matrix I'll make. Suppose you have M sources and N destinations. So my I index set of sources I'm taking as M, and index set of destinations I'm taking as, so I have M sources and N destinations. So as it suggests, right? So capitalize for that, and you have like this. This is the symbolic matrix. So this is the cost on one route per unit transportation and so on. So these are the availabilities and these are the requirements. You have A1, A2, AN and B1, B2, BN. The model which I am discussing here says that whatever is the amount, whatever you get on this route should exactly, total of that must coincide with B1 and so on. But in general, this is not the most general form of a transportation. Most general, मैं थोड़ा सा इसको distort करूँगी, because if you are asked what is a transportation problem, doesn't mean equations always. But since we are going to discuss the base model, so it could be greater than, as we did for ax less than or equal to, मतलब उसमें भी inequalities थी, यहाँ पे भी inequalities हो सकती हैं. And similarly, you could have this bj, and you have xij's for all i's. This is the model. Summation over I is this. So we want to minimize total cost of transportation subject to these conditions, right? When we get equation, then this is a balanced transportation problem. When we have inequalities, then this is unbalanced transportation problem. And for a balanced transportation, we have a UV method. Once we know how to solve balance, we can convert unbalanced to balanced and again solve that problem. So main thing is to see balanced transportation problem. Then as far as this is concerned, this is called the symbolic matrix. And what about the transportation problem? Do you think it is a linear program? इसमें कितने decision variables हैं? M into N, right? Mn decision variables and how many constraints? M plus N. See, the first set of constraints for I in I, that is the set of source constraints. Then the next set is the set of destination constraints. So there are M source constraints and N destination constraints. So M plus N. You have M plus N constraints and M into N variables. And these constraints are linear. Linear. In fact, the coefficients of these variables are all ones. So there's a typical kind of, this system, you can write this as Ax equal to B, right? X non-negative, and this A is M plus N cross Mn matrix here, right? And you are minimizing Z equal to Cx. You can write this problem like this, where what is C? C11, C12, C18, so matrix here, right? Same way that X vector is it's not a vector. You can write it in the vector form also. आप इसको ऐसे लिख सकते हैं C11, C12, C1n, C21, C2n up to CM1, CMn, and you are multiplying this with same for X. You can write it in vector form also. If you wish, you can write it as matrix also. So this is a linear program. Therefore, again, simplex method can be employed to solve this problem, right? But okay, the basic properties वही है कि यहाँ पे जो set of feasible solutions है, that is a polyhedral. Optimal solution will occur at least one of the basic feasible solutions. But these conditions were all true provided the problem was feasible. And here one thing more, I mean, it has a typical structure. One thing is we'll assure that the problem is feasible. The problem infeasible भी हो सकती है. Problem feasible है, therefore extreme point होंगे and optimal will occur at one of the extreme points. We know number of extreme points are finite. And the second thing, that this problem is a bounded problem. I mean, the polyhedron is a polytope also in this case. Set of feasible solutions of a transportation problem is a polytope. Whereas in general for an LPP, it may just be a polyhedron, it may be a polytope, it may not be a polytope. देखिए अगर polyhedron होता है, polytope नहीं है, तो आपको surety है कि problem bounded है? हो भी सकती है, नहीं भी हो सकती, या हमेशा कभी भी नहीं होगी. क्या कहते हैं? Will this problem be always unbounded? Or will it be bounded in some case? बताइए, any one of you? If the physical region is unbounded, do you call problem to be unbounded? Or the problem can graphically कैसे solve करें? Suppose my z equal to cx, आप plot करते हो इस region में. The last point of contact with the region gives you optimal solution. Suppose the line is going like this. Is there any last point of contact? No. So the problem is unbounded. It means you go on moving the line of objective function indefinitely without stopping it. Then the problem is unbounded. Suppose the objective function was like this. Suppose ये थी line. इसको आप move करते गए parallel to itself. There is a last point of contact. Then in this case the problem is bounded. Although the region is unbounded. So depending upon the line of objective function, the slope of the line of objective function, problem may be bounded or problem may be unbounded. But if the region is bounded, definitely last point of contact आएगा ही आएगा. तो problem हमेशा bounded रहेगी. So this is a very strong property of a transportation problem, that its region is, in addition to being a polyhedron, it is bounded. So it is a polytope and it is feasible also. So therefore it will have an optimal feasible solution. Feasible होगा और optimal भी होगा क्योंकि bounded है. So some properties now I'll discuss them one by one with you people क्योंकि problem solving is not going to take much time. Time minimization में आपसे बाद में discuss करते हैं. Let us discuss cost. These are the properties. So I am discussing balanced transportation problem first with you people. So first property, unbalanced हम बाद में करेंगे. So first property is that balanced transportation problem is always feasible and bounded. Why is it? I mean, I'm not going into rigorous proofs of this, but as far as simple observations are concerned, what is my problem? Let us write it this way. This is I in I and J in J. I have to say, of course, here I'm assuming that sigma AI is equal to sigma BJ. This is my assumption. Problem is balanced in this case, or unbalanced कब होती है? When sigma AI is not equal to sigma BJ. So result says that whenever this is true, then this problem will always have a feasible solution. So therefore, or whenever this problem has a feasible solution, this condition will be true. You can say that this has a feasible solution if and only if this condition is true. So therefore, when we talk of this problem, we call it balanced. क्योंकि हम इसकी feasibility की बात करें. अब देखिए इसका, अगर इसका feasible solution है तो ये condition true होगी. क्यों होगी? Let xij, let x equal to xij cap ले लीजिए, be a feasible solution of problem. Let me call this as P. It means it satisfies these constraints. Then what is my sigma ai? Then you will have xij cap is ai for j in j, and xij cap I in I will be bj, and xij caps will be all non-negative. Then what is my sigma ai over I? That is sigma xij cap over I and j, which you can interchange, over j and I xij cap, which is nothing but sigma bj. So if problem is feasible, definitely this condition is true. It's obvious. Conversely, suppose this condition is true, then can you always say there will exist some vector having in mn components such that it satisfies all this? Yes. Conversely, now let sigma ai be equal to sigma bj. Suppose this is equal to some n. This is a common quantity now because the total availability is same as total requirement. Let it be n. Define xij as ai into bj divided by n. See, it's natural. I mean, it has not been mentioned, but availability or requirements are non-negative. In fact, they're positive quantities. Each ai, each bj is positive. अगर किसी constraint में ai 0 है, तो इस constraint का कोई meaning नहीं रहेगा, because we want all xij's to be non-negative. It means all xij's are 0. So we don't have 0 here. We have all ai's and all bj's, and practically this problem makes sense only when availabilities and requirements are positive. So all ai's, all bj's are positive. Therefore n is positive. Therefore xij is positive for all I and j. And then what is? So this is positive for all I and j. And what is sigma xij? I want that this should be true, right? So j in j, what will be that? That will be, this I can take outside, bj, j in j upon n, but this sum is again n. So this is AI into n upon n. So this is AI. So I'm getting sigma xij as AI. Similarly, I can show that sigma xij over I is bj. So I can always define a solution of this kind for any problem which is balanced. So a balanced problem will always have a feasible solution. It will always have a feasible solution. Now why optimal feasible solution? Is bounded होगी तभी एक प्रॉब्लम का feasible solution है कब कहेंगे वो optimal feasible solution problem का है provided the problem is bounded, right? So how will you justify if the region is bounded? I have seen that problem is always bounded, right? So this is okay. It has a feasible solution. Can you justify that the region will be bounded? You see that each xij will definitely be less than equal to ai and greater than equal to 0, and also each xij will be less than equal to bj. Because this is required. Sum of all xij's should be ai over j's and should be bj over i's. It means looking at these expressions, each xij should be less than equal to ai and should be less than equal to bj also. Or you can say each xij, जो भी ij root पे है उसको bj देखिए. So each xij should be less than equal to minimum of m and bj's. This implies xij is greater than equal to 0 and less than equal to minimum of ai's and bj's. जो भी symbolic matrix में ai और bj दिए ij root पे जो variable आएगा, जो number of units to be transported, that will always be less than equal to, say for example, you have here, suppose you have 20 and you have 10. This is my A1 and this is my B1. This is my B1. Then what will be my X11? That will be, यहाँ मैं 20 तो नहीं लिख सकती. क्या मैं इस रूट पे 20 यूनिट्स ट्रांसपोर्ट कर सकती हूँ? क्या मैं 11 यूनिट्स ट्रांसपोर्ट कर सकती हूँ? Because I want all those units which are being transported on this route should meet this. Their sum should be 10. If I put 11 here, if I'm sending 11 units on this route, then this is violated. Okay, this thing may not be 11 plus 9, 20, but this side it is violated. तो यहाँ पे what does the logic say? कि 10 से ज़्यादा नहीं कर सकती ना मैं इस route पे, minimum. So therefore each variable, this is what I'm saying, on each route ij, xij has to be non-negative and minimum of ai and bj. Therefore each variable is bounded. तो जब आप रीजन प्लॉट करेंगे, वेरिएबल बाउंडेड है तो रीजन बाउंडेड होगा ही होगा, रीजन अनबाउंडेड नहीं हो सकता, बिकॉज नो वेरिएबल इज गेटिंग अनबाउंडेड हियर. रीजन अनबाउंडेड कब होता है? जब कोई वेरिएबल x1 x2 टू डायमेंशंस में आप देखते हैं, अगर कोई भी एक जो है इंफिनिट डायरेक्शन में जा रहा है या दोनों जा रहे हैं, बट यहाँ पे ऐसे नहीं, ऑल आर बाउंडेड. दिस इमीडिएटली सेज दैट सेट ऑफ feasible solutions is bounded. Since set is bounded, therefore this problem is bounded. So it will definitely have OFS, right? So this is what we have, that a balanced transportation problem always has a feasible solution and bounded. So it has an OFS, optimal feasible solution. Then this is clear that it has n plus n constraints and m into n variables. Then one of the constraints in balanced transportation is redundant, and number of basic variables is n plus n minus 1. See, this is an LPP. So in LPP, generally when we solve an LPP, we say let rank of A be m if this is n cross n system. And then we start with simplex technique. क्यों m मानते हैं ये पता है आपको? हमें A का रैंक नहीं पता होता, बट हम A का रैंक m क्यों लेके चलते? क्योंकि इस सिस्टम में हम आइडेंटिटी ऑलरेडी इनबिल्ट है. अगर इनबिल्ट नहीं है तो हम आर्टिफिशियल के थ्रू आइडेंटिटी लाते हैं यहाँ पे. तो वो जो ट्रांसफॉर्म सिस्टम है उसको हम x इक्वल टू b कह रहे हैं, तो उसमें आइडेंटिटी m क्रॉस n हमेशा रहती है. Therefore the rank of this matrix is n. But given a transportation problem, अब देखिए ये प्रॉब्लम है, इसकी सिंबॉलिक मैट्रिक्स है, इसमें कौन सा सिंप्लेक्स टेबल, कौन सा रैंक ऑफ द मैट्रिक्स कैसे पता करोगे यहाँ पे? But at the same time, ai's bj's may differ for a problem. Cardinality of ij's may differ as far as the system is concerned. Left hand side is the same for every transportation problem, balanced transportation problem. So we can exploit this character. So there's a fixed form of matrix A, coefficient matrix, and using that fixed form, we know that what is the rank, exact rank. In general, for an LPP, A can vary. Given the constraints, A will vary, and so you don't know what is the rank of A. But in this case, given M and N, you can see what is the rank of A, right? So that rank comes out to be M plus N minus 1. So if there are M sources and N destinations, once we know, see, we can apply the method only we know the basic variable. What is the time?